The PN junction diode. In the previous PowerPoint, we looked at p-type and n-type doping. Just a reminder of that, in p-type doping, a hole is introduced which has the effect of decreasing the resistance of the semiconductor by having majority positive charge carriers. In n-type doping, an additional electron is introduced, which has the overall effect of decreasing the resistance of the semiconductor by having majority negative charge carriers. A diode is a device that allows current to flow in one direction only. That's what makes it beautiful. When a semiconductor is grown so that one half is p-type and the other half is n-type, the product is a PN junction diode. Now, we've actually seen this before, but normally we see it with this symbol. Now, this diode will only conduct in one direction, and that is if the arrow part of our diode is connected to the negative terminal, and the flat end is at the positive terminal. And we can change the diodes to do different things. For example, ordinarily, this will conduct if it's connected in the right way, and it will release some energy, normally in the form of heat. But we can change the materials that it's doped with in order to release other forms of radiation, for example, light, as in the light-emitting diode, which you'll see has pretty much the same symbol, except we have arrows showing light is emitted. Some of the free electrons from the n-type material diffuse across the junction and fill the holes in the p-type material. This can also be thought of as the holes moving in the opposite direction. So remember, we looked at this before. The movement of holes in one direction is equivalent to the movement of electrons in the other direction. Now, because the n-type has lost electrons, it now becomes positively charged near the junction. The opposite is true on the p-type. Because the p-type has lost holes, it overall becomes negatively charged. The p-type, having gained electrons, becoming negatively charged, and the n-type, having become positive charged because it lost electrons, means that there's a potential difference in between the p-type and the n-type. We call this a potential barrier or a depletion layer. That potential barrier, which is around about 0.7 volts, is due to the separation of the charges. That is, separation of holes from the p-type and electrons from the n-type. And the voltage will tend to oppose the movement of any further charges, because potential is a level of energy, and we say that you have to overcome this potential in order for conduction to happen. It's like a wall blocking any further movement of electrons through to the p-type material. The region around that junction has lost virtually all of its free charge carriers, and therefore that region is called the depletion layer because it's depleted of charges. It's only about 1/1,000,000th of a meter wide, and it acts as a... So here's a diagram showing the potential barrier. We have our p-type material here, which has holes as charge carriers, and our n-type material here, which has electrons as charge carriers. Now, the electrons go into the depletion layer, the holes go into the depletion layer. So here we end up being negative, and here we end up being positive. So a positive and a negative here creates a potential barrier. And within that potential barrier, because the electrons and holes have combined, there are no free charge carriers. We can think of the potential barrier of 0.7 volts being equivalent to the amount of energy needed for an electron to get from the n-type into the p-type. In order to allow conduction to happen, we bias the diode. We can apply a voltage to the semiconductor, and this is called biasing. And the diode can be biased in one of two ways, either to make it conduct or to make it not conduct. In forward bias, the diode with the n-type region connected to the negative terminal of the supply, the diode conducts. The cell is connected positive end to p-type and negative end to n-type, as shown in the diagram. In forward bias, electrons from the n-type will be given enough energy from the battery to overcome the depletion layer. Remember the 0.7 volts potential barrier. So being connected to the negative terminal of the supply means the electrons in the n-type are given enough energy to overcome the depletion layer and then reach the holes in the p-type. So in forward bias, electrons continually flow from the n-type to the p-type to the positive terminal of the supply, and the holes flow from the p-type to the n-type. And that continual flow of electrons, or holes in the opposite direction, is a flow of current. Here we have the negative terminal of the supply, the positive terminal of the supply. These electrons really want to be to the positive because they're negatively charged. Each of these electrons have a negative charge. We give those negative electrons energy to cross the potential barrier, effectively squashing it. So we can see there is no potential barrier here anymore because we've squashed it down by forward biasing. And then the electrons drift towards the positive terminal of the supply, and the holes drift towards the negative terminal of the supply. The diode conducts because that depletion layer has effectively been removed. In reverse bias, we do the reverse, we do the opposite. The diode doesn't conduct when it's reverse biased, and that's when the cell is connected positive end to n-type and negative end to p-type. So we see here, here's the positive end of our battery, and here's the negative end of our battery. Now remember, this n-type here is full of negative electrons. Negative electrons want to go towards the positive, so actually they're pulled away, and this depletion layer that's in the between actually ends up getting bigger. So we end up with a larger potential gap where electrons aren't going to make the transition, holes aren't going to make the transition, and therefore conduction does not take place. In the reverse bias diode, electrons are attracted to the positive terminal while holes are attracted to the negative terminal. And so the charge carriers move away from the junction. The depletion layer becomes wider and the diode does not conduct. So we see here the depletion layer is now massive. It's got a much larger positive charge on this side, much larger negative charge on the other side, and a much larger potential barrier for the electrons to overcome. Okay, so if we have a look at the current and voltage characteristics of a PN junction, we can see here we have potential on the x-axis, and that's what's being supplied, and here we have current on the y-axis. So potential provided within one direction, this is when we are forward biased. We can see that there's not a great deal of conduction happening between 0 up to 0.5 volts. However, as soon as we hit that 0.7 volts, which is the normal level of our potential barrier, we have a large amount of conduction taking place. So the diode will conduct in forward bias, but only if we've reached a certain level of potential. If we look the other way, when we are reversed biased, again, there's not a great amount of current, but there still is some, and we call this leakage current. And that leakage current occurs due to the flow of a minority amount of charge carriers. We do, however, have a large increase within the current once we hit a much larger voltage, and that is breakdown voltage. And as we discussed before, breakdown voltage is where we're effectively destroying the material in order to make it conduct.